Good morning, everyone. Welcome to a wonderful morning of Chem 1211 with your host, me, Dr. White. Couple important things. First of all, just looked again. Seems like a lot of people are watching my videos. If you're not in my Chem 1211 class this semester, but are watching your videos, send me an email and let me know what class you're taking. I'd be interested because I'm seeing like 60 hits or views, and I only have 24 in the class. So either everybody in my class is watching my videos a lot of times, or there are other people. Now, how can you send me an email? Send the email if you're not in my Chem 1211 class to that's an awful @ sign. Send an email to whitek@cod.edu if you're watching this video and you're not in my Chem 1211 class. I just like to know about it. Plus, I can share some tips with you might have missed that are in my syllabus. All right. Now, another important thing, yesterday, the spreadsheet I showed you for the lab, when I made it up the day before, I was in a hurry and I made a mistake. Bad Dr. White. Well, I told you the first day I'm not perfect, and I'm not. And I sent out an email yesterday with the correction. And in case you didn't see it, here's the email. And the mistake I made was where it says weight of the solution. Yesterday I had density. No, it should have been weight of the solution. That's the only mistake. The step-by-step right here are correct. And this is the way you do, excuse me, you do the different graphs for yesterday's lab. So again, the mistake I made in red right here, I had density. It should be weight of the solution. And as I said yesterday, the number in front of X is your density. All right, that's taken care of. All right, a couple other things I want to mention. Don't forget, tomorrow morning, I will send out the password for quiz number 2. Hopefully, everybody, I think just about everybody has uploaded quiz number 1 answers. I haven't had a chance to grade it yet because you have until 11 this morning to finish, and I don't start before that, and I teach all day today. But tomorrow, Thursday, I'll send out the password for quiz number 2. You'll have until Friday morning, 11 a.m. to upload your answers to quiz number 2. And as I said in the announcement in Blackboard, if you're late or don't follow directions, I reserve the right to subtract up to 25 points from the quiz you're uploading or didn't upload on time. So don't forget, tomorrow you'll get the password for quiz number 2. Now, as I mentioned yesterday, I think it was yesterday or Monday, I will have all your grades for quiz 1 and 2 in Blackboard by Sunday, 1 p.m. And also by Sunday, 1 p.m., give or take a half hour, but it'll be probably earlier, I hope. I will email you an individual email for your answers on quiz 1 and 2 and how many points you got. I think for this one, I'll combine them together and do that. But that will be on by Sunday. And next Monday, I will go through the answers for quiz 1 and 2, but I will cut them out of the video. How do you like that, special effects? I mean, I'm dexterous. I can do it in stereo. All right, it's real bad humor Wednesday. But anyways, I'll have all that done Monday. We'll go through the answers and you should check. If you can't come to my class on Monday, feel free to come to my office hours. And I'm debating, I think I'll be changing my office hours. Email me at whitek@cod.edu if you'd like a different time for my office hour. Times I'm looking at is Monday, Tuesday, and Wednesday, and maybe a little later in the afternoon or early evening. If you have some time that works better for you, let me know. And finally, don't forget, hand in your labs. Labs are not hard points, but if you don't hand them in, you get 0, zip, 0, and that will hurt your grade. I saw this last semester and I taught a class and students weren't handing in their labs and it dropped their grade, a whole letter grade, in some cases 2 letters, because they weren't handing in labs. There's no reason why you shouldn't be handing in labs. All right, let's get to work. All right. Yesterday, or Monday, actually, not yesterday, I talked briefly about the VSEPR theory, valence shell electron repulsion, which the pairs of electrons want to be as far apart as possible. Oh, by the way, click, switches off. This won't be on the test. And the pairs of electrons want to be as far apart as possible. And because of that, it causes atoms and molecules, actually molecules, to have different shapes. And we talked about that. Now, let's move on. There's a very important concept that you should understand, and that's electronegativity. It's one way of saying it, or what is that? It's a measure of the relative attraction that an atom has for shared electrons in a bond. In other words, if I'm sharing an electron with you, electronegativity affects how we're really sharing it. And how do you find electronegativity? When you move from left to right, my left, my right, in the periodic table, and from bottom to top, the atoms are more electronegative. Again, when you move this way, left to right, and bottom to top, atoms are more electronegative. I should say elements, really. And let's look at a periodic table. All right, thumbs up, people. Everybody see my periodic table? Let me check. Well, you should be seeing it. All right, let's take a look at the periodic table. When you move from lithium to fluorine in any row, left to right, they become more electronegative. When you go from bottom to top, it becomes more electronegative. The most electronegative, and I don't think these really account for the noble gases, because the noble gases are not molecules. I don't know one exception where noble gas is in a molecule, because they already have an octet. But anyways, this goes from the alkali metals, left column, all the way to the halogens. The most electronegative atom or element is fluorine. And oxygen is pretty electronegative. Chlorine and bromine iodide are, but fluorine, oxygen are. Now, let's talk about what does this mean? Well, here's hydrogen all the way over here on the left. And if we look at oxygen, it's all the way under, almost all the way on the right. So hydrogen is less electronegative than oxygen. So what does this mean? Well, if we're sharing electrons, hydrogen is this weak element and oxygen is this big, strong element, big, strong. And it's saying, let's share electrons. And I'm going to share them closer to me because I'm bigger than you. And sort of like if you had an umbrella and you have a sister who's 7 years older and you're just young, like about 6 or 7, she's 14 and she's bigger than you and you're in a rainstorm and you only have one umbrella, she's going to hold the umbrella over her more than you. Sort of over you, but it's not really. Don't tell my sister I told that story. Shh. Okay. But anyways, atoms do the same thing. And example of this would be water. Water is H2O. And I'm showing water drawn this way. This is the Lewis structure. Now, here's a pair of electrons. And here's one. Now, oxygen is stronger than hydrogen, so they're sharing electrons closer to the oxygen. And how do we see this? Well, first of all, let me clean this up a little. We see this by there's a slight negative charge on oxygen, and I'll explain what the symbol is in a second, and a slight positive charge on hydrogen. That's because oxygen is more electronegative, stronger in holding the electrons closer to it, the shared electrons, than hydrogen. And this one is also true. Now, I might have mentioned this before, but this is the Greek letter delta. And it's uppercase. And in science, especially chemistry, that means difference. And we'll see later, you'll hear me say delta T, that's difference in temperature. Now, just like in our alphabet, we have upper and lower case in the Greek alphabet. And this is also delta. But this is lowercase. And this means little difference or slight difference. Which is why there's a slight negative charge on the oxygen and the hydrogens have a slight positive charge. And that's because of electronegativity. Again, in the periodic table, when you go from the alkali metals, the left, to the halogens, the right, elements become more electronegative. When you go from the bottom to the top, elements are more electronegative. And very electronegative atoms are elements are nitrogen, oxygen, and fluorine. And turns out they play an important role in our daily life. How? Well, let's find out. Now, there are different types of bond polarity, and I'm going to turn the switch click off for this. And I'm not going to ask this ever on a test, but non-polar covalent bonds, a covalent bond, which is their equal sharing. Then there's polar covalent bonds, which there's unequal sharing, like I just showed you. And here's a nicer way of delta. Obviously, my software, Microsoft Word, does a better job than I do, showing the delta plus slight lowercase delta and the uppercase, lowercase delta plus, and denotes equal sharing. Sometimes you might see it this way with a plus and an arrow. I've never used that. Think of two people sharing an umbrella. I wonder what that means. Remember, don't tell my sister. Shh. That's a true story too. I was about 6. All right. Now, there's something called polar molecules, a molecule with polar bonds that add together but don't cancel each other out to form a new dipole moment. And switches off for this. But what is on is this. I don't have a slide for it, so I'm going to do the old-fashioned way. I'll write it on the whiteboard. Hydrogen bonding, sometimes called the hydrogen bond. And that's the small and that's the small attraction. I could have put coulombic or electrical attraction between molecules with polar bonds. What this means is molecules with nitrogen, oxygen, or fluorine that have a H hydrogen on them can hydrogen bond. So hydrogen bonding or hydrogen bonds are small attractive traction, or I could have written here a small attractive force between molecules with polar bonds. And molecules with nitrogen, oxygen, or fluorine that have a hydrogen on them can hydrogen bond. And now it's time for Dr. White to be subtle. Subtle enough? Hint, know this. Water forms hydrogen bonds between itself. And if we look at, and I'll use a line to show the pairs of electrons. Here I have 2 water molecules. Remember, there's a slight charge separation. And between this oxygen and this hydrogen, I can go to a fancy color now, there's a slight attraction. It's called the hydrogen bond, but it's not a true chemical bond. It's a very weak force, and you should know water can hydrogen bond with itself. And this is very important. Why is it very important? Because of hydrogen bonding,
I'm sorry, is this 8 plus or 5 plus?
is what?
Is this 5 plus or 8?
I mean, right there,
Yeah,
that's a delta.
delta.
Mhm. Delta lowercase. Time out for all right, do you see the Greek alphabet I have on the screen right now?
Yes.
And you see where delta is?
Yes.
On the left is capital delta. On the right is lowercase delta. And that means little difference. Okay? So whenever you see that, and mine isn't too different from that, not as good as this one, but I'll talk about in this class, I'll use, I don't think I use alpha. I think I only use beta. When I was in a fraternity, pledges had to learn the Greek alphabet, alpha, beta, gamma, delta, epsilon, zeta, eta, and so on. But that's a story for another day, another class, maybe even. All right, let's get back to this. Does that help now? This right here is a slight positive charge, slight negative charge, slight positive charge. Same thing over here. And because of opposites attract, you have the delta negative attracting the delta positive. And this is called a hydrogen bond. And because water can hydrogen bond with itself, this affects the physical properties of water. And probably one of the most important is water is a liquid at room temperature because of hydrogen bonding. Room temperature, approximately 25 defined, 25 degrees C. I think that's 77 degrees F, approximately. And if you notice in my bottle here of water, it's a liquid. Now, that's because of the hydrogen bonding between the molecules of water in my water bottle. And what does that mean? If you look at similar molecular weight molecules that cannot hydrogen bond at room temperature, like in my room right now, my office, they're all gases. And if it wasn't for hydrogen bonding, water at this temperature would be a gas. And think about it. If temperature water, if what wasn't for hydrogen bonding, this wouldn't be a liquid, this would be a gas. We wouldn't have the oceans on our planet. Think about your blood, my blood, your blood. I don't know if you can see my blood veins there. There you can. And that's mainly water. What if it were a gas? We wouldn't exist the way we do now because our blood, which carries things, now I'm way beyond my knowledge of biology, because I'm a chemist, and the last time I took biology was freshman year of high school. Not that there's anything wrong with biology, but by then I knew I wanted to be a chemist, and I took chemistry, not biology, after that throughout high school and college. But that would be a gas and we'd be totally different. And there are other physical properties. I'll talk about hydrogen bonding effects during the semester. I'll talk more about it. And we're done with this chapter. Again, this was chapter 10. We're done. Now, what does that mean? First of all, on Monday, I will do both problem sets for chapter 9. I'll go through that in lecture. On next Wednesday, I'll do all problem sets for chapter 10. So make sure you do them. Keep up. Test number 1, which would have been the old syllabus, which would have been my test number 2, but because I'm now giving quizzes, is test number 1. We'll cover this material and other stuff. You have to keep up. We're getting into more difficult material. Relax, you can do it, but you have to do the problem sets and keep up. You're not going to learn chemistry a couple days before a test. Speaking about quizzes, don't forget, tomorrow I'll send out the password for quiz number 2. Well, guess what time it is? It's time for a new chapter. Wow, new chapter time. And I've jumped around because this way, and let me close something. Let me get to the beginning of the chapter. I've jumped around so it makes more sense how you learn this material, which is what I did. I went to 10, now I'm back at 6 in your book. All right, this new chapter, now we're getting to some really good stuff. See how happy I am? It's called chemical composition, and it deals with certain important aspects of atoms and molecules, and that deals with concepts we'll cover. All right, let's talk about atomic mass and mass formula. Now, switch is off right now, but this is important background information. Atomic mass of an element was defined as 1/12 of the mass of carbon C12 isotope, which is assigned a mass of 12 AMU. Now, think of atomic mass unit like you think of grams, pounds, ounces. They're all scales of mass. And they determined, chemists, long time ago, that this was a good method to help understand and be able to do a lot of things in chemistry. The concept of atomic mass. Now, from the periodic table, we can find the mass of an element, and that's in atomic mass units. And where do we find that? On the periodic table, which, everybody see the periodic table now? Thumbs up, people. Help me out. Thank you. And if you look underneath the element, there's a number. Underneath hydrogen, 1.008. That's the atomic mass, or I'll use the atomic weight. And sometimes you'll see me abbreviate AT period, WT period. And if you look under oxygen, the number is 15.999. That's the atomic weight of oxygen. For carbon, it's 12.011. And if I asked you what's the atomic weight of chlorine, Well, first of all, I have no chlorine is Cl. It's a halogen right here, and it's 35.453. Now, if you notice, these numbers have different significant figures. Like this one for chlorine is 5. And if we look over at hydrogen, it's only 4. And I'll be talking about that in a little while. Where did they get these numbers? Now, I have here, and I don't know, it's in your book, and really, let's just skip this slide. It's not that helpful. All right, before we go for formula mass, let's go back to the periodic table. If we look at hydrogen, the atomic weight or mass is 1.001. Now, to make your life easier, shh, don't tell anybody, I'm being nice. Shh. All right. On my tests, I will say, and everything we do in this class, and in real life, I've done it for doing calculations when I was in the chemical industry, that thousands, hundreds of thousands of dollars rided on me doing the calculation correctly. I use atomic weights, the 3 significant figures. My gift to you, and it is a nice little gift, little, but a gift, is for all my tests and quizzes, we will use atomic weights, the 3 significant figures. So if I look at hydrogen, which is 1.001, you should use 1.01. That's 3 significant figures rounded off. If we look at oxygen, 15.999, round that off to 3 significant figures, that's 16.0. If we look at carbon at 12.011, round that off to 3 significant figures, keep the 1, keep the 2, keep the 0, use the 1 to round off, it's 4 or less, drop that, and everything else to 3 significant figures. Carbon is 12.0. So remember, in my class, and actually in my life, I've done it, use all atomic weights, the 3 significant figures. Now, I don't have a slide for it, but because they're different isotopes of each element, the percent on our planet and our universe of each element is added up. The atomic weight mass is based on the number for an isotope, number of protons and neutrons. And for carbon, most of it is carbon 12, but there's 13 and 14, a very small amount, and that's how they got to 12.011. Now, some instructors have their students doing that. I've never done that as a professional chemist. I look at my periodic table and it shows me what it is. So let's move on. Now, there's a concept called formula mass, and I'll use the term molecular weight. And the formula mass, and formula mass, also molecular weight. Now the switch is super on. For a compound, that's the sum of all atomic masses of the elements in its formula. The molecular weight for a compound, a molecule, is the sum of all atomic masses of the atoms, all the atoms in its formula. All right, now, one thing, and I haven't changed it yet, let's look at, I have it as test number 2, but I'll change it to test number 1 before Monday next week. I have important information for the next, which was, this really should be a 1. but I can't change it in a PDF, but I'll change it. And I have what we talked about, the shells, but if you notice right here, I have the molecular weight of a compound is the sum of all atomic weights. As I said at the beginning of the semester, I have cut down on your memorization. You still have to know how to use this, but you don't have to memorize it unless you want to, because I'll give it to you. So let's look at how do you calculate molecular weight? Well, it's practice time. And let's take time to calculate the formula mass, or as I'll say, the molecular weight of water, ammonia, and sodium hydroxide. Well, how do you do that? All right, everybody see the whiteboard on your screen right now? 3 points. What is the molecular? Thank you, Anna. What is the molecular weight for a water? Well, the molecular weight is the sum of all atomic weights. And if we look in water, there's 2 hydrogen atoms and 1 oxygen atom. And now we need the atomic weights for each element. And if we look at the periodic table, you'll be given a periodic table for test 1. We'll look at hydrogen and we see 1.008. Remember, on my tests and quizzes, it will say, please round off the 3 significant figures. And that's 1.01. And while we're here, oxygen, which is in water also, is 15.999. And how do we round that off? The 3 significant figures, keep the 1, keep the 5, keep the 9. The next 9 you round off. Used to round off, it's 5 or higher. That and the last 9 you drop, increase the 0.9 by 1. That's 1.0. That becomes 16.0. So for hydrogen, 3 significant figures, the atomic weight, 1.01. Oxygen, it is 16.0. So hydrogen, the atomic weight, 3 significant figures, is 1.00. Oxygen is 16.0. 2 and 1 are exact numbers. So when I multiply it, this is 2.02. This is 16.0. And then you add them up and you get 18.02. Now we're not done. I had skipped earlier, but when you do addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. You never look at the left, only the right. So this number has 2 significant figures. This has 1 to the right of the decimal. Therefore, we have to round this off to 1 past the decimal to the right. We keep this. We look at that, that's 4 or less, I'm gonna drop it, and the correct answer using significant figures for the molecular weight of water is 18.0. Let's do another one. Ammonia. And here, the molecular weight is the sum of all atomic weights. We have 3 hydrogens and 1 nitrogen. The atomic weight of hydrogen to 3 significant figures is 1.01. And then we need the atomic weight for nitrogen. Well, where do you find that? You go to your friendly neighborhood periodic table. Everybody see nitrogen and 14.001. But on my test, I'll be asking, please round this off to 3 significant figures. Keep the 1, keep the 4, use this, keep the 0, that's my 3 significant figures. Use the next 0 to round off, that's 4 or less. So that's 0 and the 7 you drop, and to 3 significant figures, the atomic weight of nitrogen is 14.0. We multiply 3 times 1.01, 1 times, or 3 times 1.01 is this, 1 times 14.0 is this. You add them together because it's the sum of all atomic weights, and you get 17.03. We're not done yet. When you do addition, you get the same number of significant figures to the right of the decimal as the number with the lowest significant figures to the right of the decimal. This has 2 significant figures. This has 1. Which is the lower number? Hopefully I'll pick 1. So now we have to round this off to 1 past the decimal to the right. Keep the 0, use the 3 to round off. Is that 4 or less? Yes, I'm going to drop it. So the correct answer here is this. And that's how you do molecular weights. And I forgot to do this. Know this. We'll be using this for test 1, for quizzes throughout the rest of the semester, not 2, but 3, 4, 5, and 6. Test number 2 and the final. You will be asked for certain problems. You'll have to calculate the molecular weight. And let's see, do I have another one? I think I had an important one. See, sodium hydroxide. Now, how do you calculate the molecular weight? It's the sum of all atomic weights. There's only 1 sodium, 1 oxygen, 1 hydrogen. We've already learned this is 16.0, this is 1.01. And now, where do we get the atomic weight of sodium? Look at your periodic table. Remember, sodium, Na, alkali metal. And I'll give you a chance first to determine the 3 significant figures. Remember, on my quizzes and tests, after quiz 2, test 1, quizzes 4, 5, 3, 4, 5, and 6. And my test 2, it will say, please use 3 significant figures for all atomic masses. I'll take off a point if you don't. And what's the atomic weight of sodium? The 3 significant figures. Your turn. I'll give you another 10 seconds. Go. I'm looking at the clock with the seconds up above my desk here. Time's up. Sodium. How do you round 22.989 to three significant figures? Keep the 2, keep the 2, keep the 9. Use the 8 to round off. Is that 4 or less or 5 or higher? It's 5 or higher. You drop that 8 in the last 9, and the 9 in front of the 8, you increase by 1 to 1.0. 1.0 plus 22 is 22.0. So to three significant figures, the atomic weight of sodium is 23.0. And you add these all up. Oh, my first grade teacher would be happy now. He does math in his head. I did it back then too. She was happy then too. And this would be 40.01. Now, is that the correct answer? And the answer is no. When you add things, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. Now, I'm going to give you 30 seconds to figure out what's the correct answer, and then I'll do it. Give you some bonus time. If you're done, give me a thumbs up. All right, everybody's done, so I better get to work. Remember, when you add, the answer should have the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. This has one significant figure, 1, and this has 2. Remember, this is the 1s, these are the 2. Which is the lowest number? 1. So we have 1 past the right of the decimal. Keep this 1, use this to round off. That's 4 or less. I'll drop it. And the correct answer here is 40.0. So remember, molecular weight, also called formula mass, but I'll use molecular weight, is the sum of all atomic weights in a molecule. And as you see up here, if you have more than one of that type of atom, you multiply the atomic weight times the number of atoms, like in water, 2 hydrogen, you have. And if there's only 1 oxygen, well, 1 times that, and that's how you do it. Now, I just noticed someone asked me a question. For oxygen, let's do the following. If it's 15.999, how do you round that off? How do you round that off to 3 significant figures? Well, as you learned for quiz 1, keep the 1, keep the 5, keep the 9. Use this to round off. It's 5 or greater. You drop all this, increase that by 1. So that'd be 1.0, which means you increase this by 1. So that's 16.0. Does that help?
Yes, I was just a little bit confused.
You what?
Yes, I was just confused
All right, well, that's
for one
fine.
second.
My
Thank you.
class, everybody, remember, there's no such thing as a dumb question. If you don't know it, you can get confused. And that's why I'm teaching, because that way you'll learn it and get, is this a real word, unconfused? Or you'll know how to do it correctly, which is a good thing, which is why you're learning chemistry from me.
Yeah.
So remember, always feel free to ask questions. Oh, I went over our break time. Let's take a break, 5-minute break, come back at 9:57, 5 minutes from now. I'm gonna get up and stretch. See you in 5. I'm back. All right, let's continue. Now, we just did our practice time for formula mass, or that's what your book calls it, but most chemists call it molecular weight. And remember, the molecular weight is the sum of all atomic weights. And for my class, the atomic weight, or not even for anybody, is the number underneath the element in the periodic table. Like lithium has atomic mass, I don't know why 2 dots are there, but should be only one, 6.941. But as I told you, for my quizzes and tests, for quiz test 1, quiz 3, 4, 5, 6, and my test 2, underneath your name, you'll say 2 things in the future. First one is, please use proper significant figures for all calculated answers. And the new thing that will be in quiz 3, 4, 5, 6, and test 1 and 2 will say, please use 3 significant figures for all atomic masses. In case you're wondering, lithium at 6.941, the 3 significant figures would be 6.94. And you'll see when you look at the practice problems for this chapter, I have you practicing finding the molecular weight. Now, let's move on. Let's talk about the mole. And before we do that, there's something I gotta do. I don't know if I mentioned this before, but when I was in college and grad school, taking notes in the left margin of my notebook, if I wrote 3 stars, I better know that. I thought, ooh, this is real important what the instructors say. If I wrote 3 stars and important, this is super, 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 very, very important. And the mole is, what is the mole? You should know the mole is the counting unit used by chemists. What do we mean by counting unit? Well, if you go to a supermarket, can you buy 1 egg? No, it's in a box. And how many in that box or container? 12. That's 1 dozen. You know, a dozen is 12, and that's a counting unit. And if you go to a donut shop, they'll sell you 1 donut. I almost said bagel. You could do it at a bagel shop too, but a donut shop, and they sell donuts. You can buy it, they have a price. I haven't been in one in a while, so I need donuts like I need a hole in my head. I don't, so I stay away from Krispy Kreme. Is very dangerous place for Dr. White, real dangerous.
It's very unhealthy.
You're right, that's why I don't,
Yeah.
even though I love Krispy Kreme. Oh,
You could just make them like at home, like in an oven, so they will be like less greasy and heavy.
yeah, well, I just stay away from it. It's the safest thing. It's been a while since, over 2 or 3 years since I've been in a Krispy Kreme or Dunkin' Donuts. But anyways, a dozen is their counting unit. And the mole is a chemist counting unit, and you should know this. Again, it's the chemist counting unit. Now, one definition of a mole is a mole contains 6.02 times 10 to the 23rd units. And this you should know also. 1 mole is 6.02 times 10 to the 23rd. This is called Avogadro's number, and you should know that. This is called Avogadro's number. Who's Avogadro? Well, let's find out. I've never done this before. I know who he is. Here's a picture of him. Great Italian scientist back then. I don't think they called him chemist, maybe they did, who came up with the concept of atoms, molecules, and the number. And he was the one who came up with the concept of a certain counting unit. Now, at that time, they didn't know it was Avogadro's number. Two Germans came up with the final many years later, but in honor of his great achievement, they named that number after him. It should have been the Germans, but they didn't. Now, if you see right here, here it has 1 mole of a substance is 6.022140076 times 10 to the 23rd. And this is 2, 4, 6, 8, 9 significant figures. I once saw on a reputable site Avogadro's number, I think it was still 14 or 15 significant figures. Why somebody would use it like that, I have no idea. I wouldn't. For this class, we'll use the 3 significant figures, 6.02. So Avogadro is someone, a great Italian chemist, really back then they call them scientists, who came up with the concept how to measure a certain amount of atoms or molecules of a compound or an element. And we call that a mole. And a mole is 6.02 times 10 to the 23rd units. Now, this is chemistry. And I'll come back to this slide in a second. So what that means is 1 mole is 6.02 times 10 to the 23rd atoms. That would be mole of an element. 1 mole of a molecule, or is 1 mole of water, is 6.02 times 10 to the 23rd molecules of water. That's a huge number. I mean, huge. Now it's time for Dr. White to get personal. How do I get personal? My birthday is at the end of December. And my all-time favorite birthday gift I'd really like is a mole of pennies. So my birthday, you've got a number of months. Remember, all I want is a mole of pennies. What is that? That's 6.02 times 10 to the 23rd pennies. I think one time I calculated it's approximately 100 million piles of pennies, and each pile has $1 billion in pennies in it. So that's a mole of pennies. It's probably all the money that ever was, ever is, and ever will be on this planet. It's just pennies. So remember, for my birthday, just a mole of pennies. It's a lot, huge number. Divide that by 10 to the 12, and that's how many $billion or trillion, I forgot which, but it's huge. But it's just a mole of pennies. So a mole is 6.02 times 10 to the 23rd atoms of an element or molecules of a compound. Remember, 6.02 times 10 to the 23rd is Avogadro's number. Yeah, well, the lottery wouldn't even cover that. Even if it was $1 billion, it wouldn't cover that. A mole of pennies is a lot more, Anna. All right, now, as I mentioned, I have cut down on the memorization of things for this class. You have to know how to use them, but in the past, students would have to memorize what I've just highlighted in blue, that 1 mole of an element is equal to 6.02 times 10 to the 23rd atoms of that element. 1 mole of a compound equals 6.02 times 10 to the 23rd molecules of that compound. You don't have to memorize it. This will be an important information. I'll have to change the number, test number 1, which is coming up in a couple of weeks, but we got time. And that's a good thing. I'll be testing your knowledge of how to do chemistry, not your knowledge how to do chemistry, and testing your memory.
So from that, we just need to know that it's Avogadro's number.
Well, I'll explain why, but
Okay.
well, you also either have to know what I have in blue, or you have to know you can find that in the important information. But you do need to know 6.02 times 10 to the 23rd is called Avogadro's number. This is one of the most important things in chemistry, the concept of a mole.
Okay, perfect.
I mean that in chemistry, the concept of a mole is probably one of the most important things. Now it's time to do some math. Everybody take a deep breath. Let it out. Take a deep breath. Relax, let it out. Take a deep breath. Relax, let it out. Are you all relaxed? Now we're going to do some math. Relax. We're even going to this semester do some algebra. I will teach you and practice with you. The math will do, but you've got to practice on your own. But it's doable. Relax, just pay attention, and you'll get it. And it won't be that painful, like hopefully 0 pain. Now, you may or may not know that if I have 2 things equal to each other, come on, A equal B. When I have 2 things equal to each other, there are 2 ratios you can draw or determine. And that's when this is the case, you also know this is true, A over B, and not equal, they're separate, B over A. Whenever you have 2 things equal to each other, there are 2 ratios. Whenever 2 things equal each other, there are 2 ratios you can have, A over B or B over A. So what does that mean for chemistry? Well, here I have it written here, but I'm going to write it on the whiteboard, which you'll see easier to see. Now, we know, as I told you this, 1 mole of an element equals Avogadro's number. And what's the unit of elements? Atoms of that element. So from this, I also know 1 mole of an element for 6.02 times 10 to the 23rd atoms of the element. That's A over B. And I know the other ratio, 6.02 times 10 to the 23rd atoms of the element per 1 mole of the element. Now this you have to memorize yourself. And what do you have to know? That is, if two things are equal, there are two ratios. You actually really don't have to memorize this, but it'll help. So if I have 1 mole of an element equal Avogadro's number, 6.02, there's a decimal point there, now you can see it better, times 10 to the 23rd atoms of that element, I have two ratios I can draw. Now the same is true for 1 mole of a compound. That's equal to Avogadro's number, 6.02 times 10 to the 23rd. Now, compound is made up of molecules. So for a compound, like water, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd. So just as if A equals B, there are two ratios you can have. There are two ratios I can have here. And the first one is 1 mole of a compound. If I can spell it right, per Avogadro's number, molecules. Of the compound. And not equal, two separate statements, the reverse, 6.02 times 10 to the 23rd molecules of the compound per 1 mole of the compound. So whenever you have two things equal to each other, this equals this, you can have two ratios, which I did. The right, the left over the right, and the right over the left. And as I said earlier, in important information, I will give you 1 mole of an element equals 6.02 times 10 to the 23rd atoms of that element, and 1 mole of a compound equals 6.02 times 10 to the 23rd molecules of that compound. And remember, the mole is the chemist counting unit. Just like a dozen, let's go with something a little healthier, a dozen bagels. Not that it's that much healthier, they're also fattening too. Bagels are dangerous too. But Dr. White loves garlic or onion bagels. Oh, good. But anyways, these will be given to you. And that's how I derived these two statements. When you have 1 mole of a compound or element equals Avogadro's number of atoms or molecules, you have these two ratios. So it's mole practice time, including unit analysis. Now, unit analysis is your good buddy, your good friend for this semester, unit analysis. Unit analysis has been my good buddy, my good friend for many, many decades. Actually, I learned unit analysis in my senior year of high school in advanced placement chemistry by the chairman of the department of the high school science who was also the chemistry teacher. I still remember him, great man, Dr. Ernest, or not Dr., he was Mr. Ernest Solomon. And Mr. Solomon taught us, all the people, unit analysis. Really, he beat it into our head. It's like, you know how to breathe, you know how to use unit analysis. It's just that basic of your personality it becomes, and has been in mine, and I'll be forever grateful. Now, what's unit analysis? Unit analysis is a way of determining how you set up, excuse me, a solution to a problem, and it helps you, guides you what to do, and it makes your life easier. And all my students who have learned unit analysis, which are most of them, do real good in chemistry because it makes their life easier and gets better grades, which is a good thing. And they learn this. So let's do some practice. Now, let's show basic unit analysis. And this is not chemistry. Now, this is called a word problem. Relax, watch how I deal with this. First of all, what are we trying to find? And I put a question mark, how I evolved that. I don't remember, I've been doing it so long. We're trying to find how many eggs. You put down the units of what you're trying to find. Then what are you given? 2 dozen eggs. And what do you know? 12 eggs equal 1 dozen eggs. So how do you use unit analysis? Once I've read the problem and done this, I no longer have to look at the problem because this will help me right here. And how do you use unit analysis? Your good buddy, your good friend, unit analysis. Let's see how many times I can do this the rest of the semester. Lots. And what do we have to start with? Well, the only number we're given is this. We have 2 dozen, and I should have put down eggs. And we want to get what units to our final answer should be. We want it in eggs. Oops. Now watch closely. Here's unit analysis and how it works. If there were a ratio, I can convert dozens of eggs to eggs. What would that ratio be? Well, here's how you use unit analysis. Whatever I'm trying to get to, units go on top. Whatever units I'm trying to get rid of go underneath. This way, I'll convert the units I start with to the units I want to get to. Again, whatever I'm trying to get to unit-wise, I put on top of this ratio. Whatever I'm trying to get rid of goes underneath. Now, where do I get these numbers? From this right here. And up here, first of all, I'll put in the units. And remember, when you have 2 things equal each other, you have 2 ratios. And here, notice 1 dozen eggs equals 12 eggs. So 1 dozen eggs equals 12 eggs, or 12 eggs equals 1 dozen, which would be one of the ratios, one of these 2 ratios. Now, another important thing in math is if I have two things divided by itself, they cancel out because they equal the number 1. Two things divided by themselves, the same thing divided by itself becomes the number 1. So notice here, if I multiplied this to units here, I would get dozen eggs times eggs divided by dozen eggs. And notice these two are the same. A divided by A is 1. And this means my units will end up in just eggs. Well, that means everything's working. I do the math. And as you know, the answer is 24 eggs. And this is unit analysis. And it will be your good buddy, your good friend, unit analysis. All right, let's get to chemistry problem. Depending on my mood, 4 or 5 points. And the question is, how many atoms, AU is gold, are 6.37 moles of gold? So how do we do this? Well, the first thing is, what are you being asked to find? How many atoms gold are there? So we're trying to find atoms AU. What are we given? Well, this number, 6.37 moles of AU. So now it's time to use your good buddy, your good friend, unit analysis. And how do we set this up? Well, if we look up here, the only number I have to start with is 6.37 moles, and it's important to write down the units, moles of gold. And what do I want my answer to be in? And I put an equal because I want this to come out to be in that units, atoms of gold. And now, what do? I use unit analysis, your good buddy, your good friend. I think you heard the whistle enough. And if I had a ratio to multiply this number to convert it to my answer, what would that ratio be? And this is where you use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of, unit-wise, goes underneath. And now I will write those units. So I need a ratio of atoms of AU to moles of AU. Where do I get that? Well, if you look at important information, I've got to change the number. I will by Monday of test number 1. It's right now test number 2, but it'll be test number 1. It says 1 mole of an element equals 6.02 times 10 to the 23rd atoms of that element. Now, you don't have to write it on the problem, but I'm going to write it so you remember where I got it. I got from important information. So whenever you have one thing equal another, there are two ratios. And if I have how many moles of gold? 1 mole. How many atoms of gold are there? 6.02 times 10 to the 23rd. And now before I pick up my calculator, I'll see, do I get the right units? Now notice I have moles divided by moles. Remember, anything divided by itself equals the number 1, cancels out. So this unit is gone. And what am I left with unit-wise? I haven't picked up my calculator. I lied, I didn't pick this up yet, but I get the right units. And if you don't get the right units, you're not going to get the right answer. Now, important thing, this is a definition. And the 1 is a define. This is 3 significant figures. Avogadro's numbers are calculated. So the 1 here is an exact number. And exact numbers do not play a role in calculating how many significant figures your answer should be. And how many should be? When you do multiplication division, in this case multiplication, the number has the same number of significant figures as the number you're multiplying or dividing that has the lowest significant figures. 6.37, 3 significant figures. Oh, Avogadro's number, 3 significant figures. So my answer should be 3 significant figures. I turn on my calculator. Don't forget, for 10 to the 23rd, blue double E, second key double E. My calculator gives me this number. Well, this is 2, 4, 6 significant figures. I have to round this off to 3 significant figures. So I keep the 3, keep the 8, keep the 3, use the 4 to round off. Is that 4 or less? The answer is yes. So I drop all of this, and the correct answer is 3.83 times 10 to the 24th atoms of gold. And that's how you use your good buddy, your good friend, unit analysis. Now, on my, everywhere I work, I always put the units of the answer where I put atoms of gold. If you just put the number, round it off correctly, I'll give you full points. Now, important thing in even quiz 2, but test 1 and 2 and quizzes 3, 4, 5, and 6 show your work. If you make a mistake, and so 5 or later on we'll have 10 and one problem will be 15 points, and I say, oh, that's a minor mistake, I can give you partial credit. If you do not put down and show your work and you get it wrong, just put an answer down and it's wrong, you get 0 points, which is one of the reasons I don't like multiple choice, and I only use a few on some of my quizzes and tests. Because if you're doing a problem like I just did, you make a math error because you wrote down or just pushed the wrong button on your calculator on a multiple choice, you get 0 points. On my test, if you show your work, you get most of the points. On a large problem, if you make a math error, I just take off 1 point instead of giving you 0. So it always pays to show your work. All right, let's go through this again. The question is, say 5 points. How many atoms, gold, that's AU, are 6.37 moles of AU? When you see a word problem, relax, take a deep breath, you can do it. You have to figure out First of all, and you show it by with a question mark, you can use whatever you want. What are you being asked to find unit-wise? Atoms of gold. What are you given? Well, this is the only number, 6.37 moles of gold. Once you've calculated this, it's time to use your good buddy. Oh, that was awful. Let me try it again. Time to use your good buddy. That's better. Your good friend, unit analysis, and it will be your good buddy, your good friend. You put down, the only thing you have to start with is 6.37 moles of gold. You look up here, what units do I want my answer? And it's atoms of gold. And therefore, you use your good buddy, your good friend. You have a ratio that will convert moles of gold to atoms of gold. What's that ratio? Well, to figure it out, whatever units you want to get to goes on top of the ratio. Whatever units you're trying to get to, follow the red arrow, goes on top of the ratio. And whatever units you don't want, you want to get rid of, go underneath the ratio. And then where do you get these numbers? Well, you've learned, and this will be an important information, 1 mole of an element equals Avogadro's number, 6.02 times 10 to the 23rd atoms of an element. So the ratio, moles of an element, 1. Number of atoms, Avogadro's number. Then notice moles of AU divided by moles of AU. Anything divided by itself equals number 1. It's gone. And I'm left with atoms of AU, which is my answer. And we now do the math. Remember, 1 is an exact number, and 6.02 times 10 to 6.37, 3 significant figures, 6.02 is 3. Our answer is 3. Now, let me show you how unit analysis also tells you, oops, you made a big mistake. First of all, let me do this. This is wrong, but this is how unit analysis will tell you. Let's say you have moles of AU, and you want to go to atoms of AU, and for some reason you do this backwards. Trust me, I've seen this. And this usually happens when students don't put in the units. Well, this gets you to that, and the answer is no. What it does get you to unit-wise is moles of AU times moles of AU divided by atoms of, in this case, gold AU. Is that what we want the units of our answer to be in? Moles of AU times moles of AUs? And the answer is no. And this also shows you that when you look at your units, that's why it's called unit analysis, analyze what cancels out, you'll see that's wrong. And this one is correct. All right, let's do another one. All right, 5 points, or it could be even more, 6 or 8, depending on my mood. How many moles sodium remember Na is sodium, are 7.145 times 10 to the 28th atoms of sodium. Now, we're going to do this stepwise, and I'm going to have you try it, and then I'll show you what's right. When you're done, give me a thumbs up. Right here, put in, what are you being asked to find? What are you given? That's all I'm asking you to do right now. Your turn. Figure out, what are you being asked to find unit-wise, and what are you given? When you're done, give me a thumbs up. All right, looks like everybody's done. So what are we being asked to find? How many moles of sodium? So I like putting a question mark, moles of sodium. What are you given? This number. There's 7.145 times 10 to the 28th atoms sodium. Once I have this, I never have to look back at the problem. So I won't. So it's time to use your good buddy one more time, your good friend, unit analysis, and it has been mine for many years. How do you do that? Well, whatever you're given, you start with. Don't forget to put the units. Then what are we being asked to find? And we figured that out. You put the units. Now, unit analysis, your good buddy, your good friend, to convert from this to this, you use a ratio. Now, I'm going to let you just put the units, not numbers, above and below the ratio you should do. Use your good buddy unit analysis. You try it, and then I'll do it. And give me a thumbs up when you just put the units, not the numbers. All right, looks like everybody's done. So it's my turn. And using your good buddy, your good friend, whatever you're trying to get to, units go on top of the ratio. Whatever you're trying to get rid of, units go underneath. And now I'm going to write those units in. All right. For some reason, I'll have to do it in red. Let me try again. There we go. For some reason. So on top goes moles of Na, underneath go atoms of Na. And where do we get that ratio? 1 mole of an element equals Avogadro's number of atoms of the element. And this will be given to you in important information, test number 1. Right now in the Blackboard, it's called test number 2. I got to go in there before next Monday and change it. So your turn. What number goes on top? What number goes underneath? Your turn. And when you just put the numbers in, I'm not asking you to do the multiplication division, just put the numbers in there. Give me a thumbs up. All right, looks like everybody's done. And where do we find in this ratio? Remember, if A equals B, you have two ratios, A divided by B and B divided by A. And here's my equal, two things equal each other. And for every 1 mole, where do I get that 1? Right here. There's how many atoms? 6.02 times 10 to the 23rd. Now, before I pick up my calculator, I'm not going to even pick it up because then I would have picked it up. And I said, don't. I look at my units. Notice atoms of Na divided by atoms of Na. When you have two things divided by itself, A divided by A, they cancel out because they become the number 1. So this cancels out. What units am I left with? Moles of Na, sodium, which is I want, the number I want. So now I can happily pick up my calculator. Happily. Oh, that was awful. Turn it on, clear it. I have 7.145. Second key, double E on my calculator to get 28 divided by 6.02, second key, double E, 23. Oh, and my calculator, I got enough room to write this, 1.186877076 times 10 to the 5th. Well, remember, and I multiplied that by 1, you know what that means. Anyways, this has a division. When you multiply and division, you have the same number of significant figures in your answer as the number that has the fewest significant figures in your answer. Well, this one, remember, all non-zero numbers are significant. That would be 4 significant figures. Here, Avogadro's number is 3 significant figures. The 1 is part of the definition. It's an exact number and does not play a role in significant figures. So when you do multiplication division, your answer should have the same number of significant figures as the number that has the fewest significant figures. Which is smaller, 3 or 4? Time's up. Hope we all pick 3. Now I'm going to give you a chance, then I'll do it. Round that off to 3 significant figures. Round off 1.186877076 times 10 to the 5th to 3 significant figures. Your turn. And when you're done rounding off, give me a thumbs up. Everybody done? Thank you. All right, let me do it. All right, the 3 significant figures, keep the 1. All non-zero numbers are significant. Keep the 1, keep the 8. That's my 3 significant figures. Use the 6 to round off. Is that 5 or higher? Yes. So I'm going to drop all of this and increase that by 1. And you get 1.19 times 10 to the 5th moles of sodium. You should know how to do these. They're practice problems. We'll do more of them. If I look at my clock, we're just about out of time. But let me just go through this one again. But before I do, let me quick reminder, remember tomorrow, I will be sending out in the morning, I think about 8 or so, 8 a.m., the password for quiz number 2. You download that. You should be able later this afternoon, download it, the PDF file that's password protected from Blackboard. And then tomorrow, once I send out the password, you can take it. Don't forget, upload it as a single PDF file. And if you're late or don't do it correctly, I reserve the right to subtract up to 25 points. So please be on time. It's due Friday morning by 11. And if we go back to our problem, I wanted to get that in before we finished, and I did. We look at our problem, how many moles sodium are 7.145 times 10 to the 28th atoms of sodium. You find out what are you being asked to find unit-wise. That's why I put the question mark, moles of sodium. What number are you given? And sometimes you're given more than one number, but for now, this is the only number, 7.145 times 10 to the 28th atoms of sodium. This is the only thing we have to start with. What units do I want my answer in? We figured that out. And then this ratio will convert atoms of sodium to moles of sodium. And you use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio of the units. Whatever I'm trying to get rid of goes underneath. Where do I get these numbers? From the fact that 1 mole of an element equals Avogadro's number, 6.02 times 10 to the 23rd elements. And you know there are 2 ratios. So from 1 to ratios, 1 mole of sodium equals Avogadro's number, 6.02 times 10 to the 23rd. Units cancel out, do the math, and we're done. And we are done. And with that, I'm going to say goodbye. Gehen gesund. I'll see you on Monday. Don't forget, on Monday, we will do the practice problems for chapter 9, and we'll continue on with this good stuff with the mole. Don't forget, do the lab. When you're doing the lab, wear your safety goggles and gloves. If you need to, your apron. With this one, we're just dealing with popping water and sugar. And don't forget, as I said yesterday, the cheapest place to find sugar, if you need it, is Walmart. And with that, I'm done for today. I'm done for the week. Don't forget, today from 5 to 6:15, I'll have my office hour. And also, if you'd like a different office hour time, Monday, Tuesday, or Wednesdays later, email me and I might change it. With that, gehen gesund. Goodbye.